Hey, Mr. Leong, what are you doing?
I'm playing Genshin Impact. I'm trying to beat the boss.
Oh, hey, I like this game. Oh. Hey, boss, go,
okay.
go.
Faster.
Hey, you don't know lah, like
Hey,
that.
hey.
Like that.
Oh, hey, no bad.
Faster.
Okay. Relax. I need to wall plug, please.
Hey, interesting wall plug nowadays.
Okay, play. Okay.
Go, there. Go.
Ah! High five.
Yeah.
Okay. Good. We are done with the game already lah. Okay. So we can finally study already. Right? Okay. Woke up very annoying. Okay. So actually, what we are doing just now, right, is we are actually doing a electrochemical cell. We're doing electrochem altogether, right? What we are doing when we're playing the game is that I'm actually simulating an electrochemical cell. What do we have in the phone is actually a battery, and the battery is powering up my game. So in this case, we can actually see this in the diagram over here. This will be an electrochemical cell. But on the other hand, when the phone runs out of battery, right, what does it become, Mr. William?
You use the power socket, correct? So
yes.
the power socket is going to draw out electrical energy to try to recharge the phone, right? So it looks like electrical to chemical energy, so that is actually an electrolytic cell.
Okay, so that means that they are actually opposites of each other, is that right? So when I'm playing the phone, I'm using the chemical energy to convert it into electrical. That is the role of an electrochemical cell. And on the other hand, when I start charging it, it is the other way around instead.
Yeah, so this is what makes a battery rechargeable.
Okay, so how about this? Let's go into our notes and then we're going to see a simplified diagram and as well as to recap a little bit about what we have learned in Electrochem so far. Let's look at the encyclopedia. So this is on page 90 of the notes. What we're going to do is, in the context of the phone just now, we're going to use a simplified diagram that we saw in our notes earlier to represent what's happening inside the phone. Okay, so let's just recall that if you're using the phone, basically the battery in your phone is going to give you the energy, the electrical energy, right?
Yes.
So we are in fact turning chemical energy into electrical energy. The chemicals will come in the chemicals will be here, and the electricity will be coming in through the external circuit. So what we are seeing over here is that your chemical energy is going to turn into electrical. Mr. William, is this a spontaneous or a non-spontaneous process? What do you think?
It looks like if I leave the phone over there, it's just going to run, right, until the battery is flat.
Correct.
So I would think that this is like a spontaneous reaction.
That's good. So in the context of electrochemical cell, we say that the E cell is going to be positive and your delta G would always be negative. That's an indication of spontaneity, right? So on the other hand, right, when we look at the electrolytic cell, now what's going to happen is that my phone now finally runs out of battery. So I'm going to use a power plug, right? We're going to plug it into the wall and then we're going to use the electricity from the wall to help me to generate the chemicals, right? So we're going to pass it on to the chemical energy. So in this case, this will be exactly the opposite from electrochemical cell. So in this case, Mr. William, do you think this will be a spontaneous or non-spontaneous reaction?
It cannot be spontaneous. I mean, if it's spontaneous, then we don't need to charge anymore. It will auto-charge, right? The fact that we're using external source of energy will mean that it doesn't happen on its own. So this is definitely not a spontaneous reaction.
That's right. So you always need an external power source, right, to power up my stuff. So in this case, your E cell would definitely always be negative for any electrolytic cell. Your delta G will always be positive, right? Now, shall we move onto something a little bit more technical? So in the event that you are, sitting for exam, if you're encountered with a question that's electrochemical cell, Mr. William, can you run us through what are the methods that you're going to use to help us to solve the problem?
Yep, sure. All right. I think the whole thing is you're very tactical right now because electrochemical, there's one thought process and then electrolytic, there's another thought process. Okay, so let's be very sure what happens. Now, in an event you're given an electrochemical cell, one of the key things you look for is like the voltmeter, right, to suggest that electricity is being produced. So what we usually will do is we'll compare the equations on both half cells and we have to decide who is going through oxidation and who is going through reduction. So if you compare this with the data booklet, you will notice that the zinc 2 plus half cell, they will prefer to undergo oxidation and therefore this will be the anode. On the other side, this will prefer to go through reduction and therefore this will be the cathode. So it's all dependent on who is more positive, right? More positive should favor reduction and less positive should favor oxidation. So that's usually how we kickstart the thought process when it comes to electrochemical cell.
That's right. Yes. So we always remember that cathode always undergoes reduction, right, using the red cat. And if I talk about electron flow, we say that your oxidation half cell, you're always releasing the electrons, right? Because oxidation is defined as a loss of electrons. So your electrons will always flow from the anode, the oxidation half cell, all the way to the cathode.
Yep, that is right.
So these are the general thought processes, right? Last of which is always to calculate the E cell, which is always using E reduced minus E oxidized.
Yeah, definitely it must be more than 0.
That's right.
Yep.
Now, what happens if I look at a electrolytic cell then? Now, the methods will be definitely different now. Okay, so we can't always say that something that's more positive will give me a reduction. So we have to follow a series of steps over here. Now, first of which, you must understand that, electrolytic cell, it always depends on the polarity of the battery. The minus terminal, which is the shorter end of the battery, will always be connected to the negative terminal of the electrode. Okay, and conversely, if it's positive, then you'll connect to the positive one, right? Then in the negative electrode, we will say that opposite charges always attract, which means that cations will flow towards that, right? And cations, they can only undergo reduction, and that is why we call the electrode the cathode. So the converse will be true as well. So the positive terminal is going to attract the anions. Anions migrate towards the anode, and in this case, anions usually undergo oxidation, so therefore we call it the anode. Okay? All right, Mr. William, can you run us through the standard series of steps, right, that help us to determine at each electrode what kind of reactions are going to happen?
Okay guys, now if you look at your notes, we're going to use some examples to run through the thought process again. Now if you look at scenario 3 of your notes, it is stated over there that we are going to do this under concentrated sodium chloride using graphite, which is a type of inert electrodes. Now, so what we're going to do for the class is we're going to combine 2 scenarios into one. Instead of just focusing on concentrated, we're going to talk about number 1, what if it is aqueous? It means it's not concentrated. And number 2, what if it is under high concentration? The thought process will be slightly different. Okay, so let's begin with aqueous. Now, imagine you're given aqueous sodium chloride. The very first thing we do is we focus on the electrolyte and we ask ourselves that question, what are the species that is present? So Mr. Leong, can you tell us what species are present?
So NaCl, ionic substances that are soluble in water, they dissolve to give me ions. So you have Na+, Cl-, as well as the solvent, right, which is going to be water.
Okay, so let's write this down. We have Na+, Cl- as well as water. Now, after you have identified the species present, next thing is to decide where do they travel to. Just remember, opposite charges will attract. So Mr. Leong, if I'm a cation, where will I go to?
So cation always migrate towards the cathode, which is negatively charged, right? Opposite charges attract. So similarly, your chloride ions, your anions will migrate towards the anode, which is going to be positively charged. Now, water is the solvent, so it's going to be everywhere. So both the cathode and the anode, they'll be present there.
Okay. Now, after we have done this, you know that different species will move towards different terminal. The next thing we're going to do is we're going to focus on individual terminals.
Yes.
Right? So at the cathode, can you tell us what's going to happen?
So at the cathode, there are going to be two species, right? You have your Na+ and your water, and they are going to start to compete to see which one is going to be preferentially reacting. So they're going to compete. So okay, so when I look at cathode is where you see reduction. And can you remind me again, Mr. William, reduction, right? Which E0 will be preferred? Will be the higher or lower one?
Yeah, if it's reduction, we're looking for the higher or the more positive to go through the reduction process.
Okay, so we're looking out for the one that's the higher E0, right? So in this case, I'll write out the half equations for both the species that are present, Na+ and water, right? So we're looking at reduction, so we have to choose the equation that water is on the left-hand side, okay? And you see that, hey, which one is actually higher, Mr. William? Careful, careless mistake.
Higher means more positive.
Okay.
Correct. So we're not looking at the numerical value, right? But we're looking at a mathematical more positive value, right?
Yes.
Which is negative 0.83.
Yes, be careful. So we're actually looking out for this one over here. Okay. This means that your water is going to get reduced. Okay. What happens now if I start to change it up to become concentrated sodium chloride? You're going to see something's going to be different now, right, Mr. William?
Concentrated means it's no longer aqueous, right? So I think water is still present.
Okay.
But it's in smaller quantities,
right?
And it's concentrated means it is beyond that standard reference of 1 mole per dm cube. So let's deploy Le Chatelier's for this understanding, right?
Sure.
So I'm going to increase the amount of Na+, and that is probably going to shift equilibrium 1 forward,
yes,
right? And shifting this forward means that I'm going to make this E0 value more positive.
Okay, wow, that's a bit confusing. So more positive, negative 2.71, they're going to increase to a value probably around, let's say, negative 2. Okay, so this is an arbitrary value. It's not a fixed value, but we're just going to make it negative 2. And then we're going to start to compare again, right? We're still going to use the same method to see which one has a higher E value now, okay? Mr. William, who is still higher?
Negative 0.83 is still higher.
Yes, okay, so you realize that even though Na+ has higher concentration, right, you still notice that water is still going to be preferentially reduced. Okay. Does this happen for the anode as well, Mr. William?
Well, let's take a look. You know, anode is a slightly different thought process.
Okay.
So what we understood is that your Cl minus is going to travel there, going to do oxidation. You also have water traveling there. So just be mindful, this equation is different from the other one because water is going to get oxidized, right? And at the anode, it will be slightly different, right? So who is preferentially going to get oxidized?
So I'm looking out for the one that has a lower E naught value or more negative, right?
Okay, so I'm just going to put here a lower E naught value. So now let's look at aqueous medium first. Now I have these two values. Which one looks lower to you?
This one's simple lah. Should be the second one, 1.23.
Okay, so the second one, I'm just going to underline this. This preferentially should be discharged. It is under aqueous medium.
That's right.
But again, if you're doing concentrated NaCl,
okay,
we're
so
going to increase the amount of Cl minus, right?
That's
and
right.
What's going to happen?
So you start to see that water is present in small amounts, Cl minus is in higher concentration. We have to apply LCP again, right? So if I take a look, high concentration of Cl minus, it should shift the position of equilibrium towards the left, right? And what happens to the E naught value is that it's going to start to decrease. So let's take an arbitrary value again. Let's say you decrease to, let's say, negative 1.2 lah. Okay.
Positive 1.2.
Positive 1.2. Yes, you're right. So if it's positive 1.2, we are going to apply the same principles again. We're going to see which one has a lower E value now, right? In this case, Mr. William?
You can see that this time round, there is a change, right? It's like this guy is decreasing and now it's decreasing to an extent that is even smaller than the positive 1.23. And since we are looking for the one that is lower E naught value, then that will mean that Cl minus is going to be preferentially discharged.
Right.
So there's a change in outcome by going from aqueous medium to concentrated medium. So it's very confusing, right? Sometimes it looks like there is a positive difference, you know, and sometimes it doesn't look like there's any significant difference. So eventually, what do we look for?
We're looking out for the difference in your E naught values, right? So if the values are way too different, for example, the first one, the numbers are, almost 1 point something. So you realize that the difference is way too large to decrease and then surpass the whole value altogether. So therefore, we are not going to see a change in terms of what is being discharged. But if the numbers are pretty close, so 1.36 and 1.23, then the change due to the LCP would cause a different product to be formed. Right? So for the context of A levels, you realize that only the chloride ones will be the ones that will change. Other than that, your bromide iodides will not change as well.
It's very similar to studying, right? If you're lagging way too far behind, you chong towards the last stretch, you get a little bit of boost, you're still not going to get your grades, right?
Yes, that's right.
But if you're lagging by just a little bit, if I give you the shuttlers, you will get your A grade.
Okay,
correct?
so
good analogy?
Good analogy. So must drink more salt water, is that what you mean?
Yes.
Oh, okay, can. So these are all done under the inert electrode, right? We're using graphite. But what happens if I decide to be a bit funkier? I decide to use a copper electrode. So in a context, I think in different electrode, it might become reactive instead. Right? So we're going to use back the same example. We're going to use scenario 4, right? Let's take a look at what happens when we use copper sulfate as the electrolyte now.
Okay.
The methods have always been the same, right? The first step is always to look at the electrolyte and determine what are the ions that are present.
That's
So
right.
Mr. William, now it's your turn to remind me what ions are present here.
Okay, so we have copper 2+, we have sulfates, and we also have water.
That's right. So who is going to migrate towards the cathode?
Cation ions always go to the cathode, anions go to the anode,
Right.
Water travels to both.
That's right. Okay. Now, let's take a look at one of the electrodes now. So we're going to take a look at the cathode, and cathode always undergoes reduction, right?
Yep.
So I'm going to write out the half equations for the ions that are migrating towards the cathode, and they are here. So you're going to have your copper 2+, you're going to have water over here, right? So Mr. William, who is going to react now?
The one that's more positive, so I can see that copper 2+ is more positive. That's why there's a tick to that.
Okay, so the copper 2+ from the electrolyte is going to undergo reduction to give you your copper solid. So they're going to start to deposit more and more copper onto the electrode. Okay, what happens now if I look at the anode then?
Okay. Now before we go to the anode, the cathode, I thought copper is active. Then why didn't we talk about it?
Oh, good question. So when we talk about copper, copper is a metal, right?
Yes.
So metals usually they undergo reduction or oxidation.
Metals should get oxidized.
So there's no such thing as copper undergoing reduction, right? So therefore, this is a very important note that if I look at the reduction electrode, the cathode, right? Even though your copper is there, the copper cannot undergo reduction. So it is going to be like considered as an inert electrode there. So therefore, even though you change it to something that's more reactive, it will not nothing will happen at the cathode itself.
Okay, so active metal is useless lah.
Yes, correct. At the cathode lah.
Okay,
Yes.
I see.
Does it apply for the anode?
anode is where oxidation takes place, so there's a chance they may get oxidized. So we cannot say that they're inerts, right?
Okay, so therefore we have to start to consider their half equations there as well.
So they will take part in that competition as well.
That's right. So it becomes a three-way match lah.
All right, okay.
Okay, so if I take a look at the anode now, anode is where your oxidation takes place. So when I write out the half equations, right, we also obviously have to write out the ions that are present there, which is going to be water as well as our sulfate, right?
Yep.
Okay, but because just now, like what Mr. Williams said, copper is going to be reactive, so we're also going to write copper over here. Okay, so Mr. Williams, can you run us through what's going to happen from now on?
Okay, so we are looking for the one that is undergoing oxidation, all right? So the one that is going to be more negative or lower E0 value should undergo the oxidation process. And I think you can see from the values that this is the one that's going to be the most negative, right? So in this case, copper selectively went through the oxidation process. Okay, so I think from this exercise, it is not a guarantee that an active electrode must get oxidized.
That's right.
Right? So it basically the whole thought process is it still joins in a competition, right? They are all always competing to get oxidized, and it's really a matter of the values. Whoever is more negative is going to go through the oxidation process.
That's right.
Hey guys, the next thing we're going to look at will be a lot of physics, which is something that I really dislike. Do you like physics?
I don't like physics as well, unfortunately. I only like math, yes.
Okay, I only like Chem.
Oh, okay.
Okay, anyway, I'm not very good at physics, but I'll just get a job done to focus on what is important in terms of the calculation. Alright, so Mr. Leong, let me ask you a question, right? Let's say we have this equation over here. You can see that copper, 2 plus is going to change to copper. So what does it take for me to have more copper?
Oh, you want more copper, huh?
Yes, I want more copper.
Oh, more copper. I mean, if you look at the equation, if you ask me to look at the equation, to get more copper, I think I need to have more electrons, right? Okay. So that by mole stoichiometry, I realized that I can get more moles of copper as well.
Okay, and how do I get more electrons?
Probably supply more energy, more electrical energy. I probably want to have more electricity. I think that hopefully helps me to give me more mass.
I see, I see. So you're trying to say that the amount of copper that is formed is only dependent on the amount of electrons.
That's right.
So will things like concentration, if I increase the concentration of copper 2 plus, does it help to give me more copper?
If I think about this, more concentration means more Cu2 plus, right? It feels like more Cu2 plus should give you more copper. Is that right?
It sounds right, but let's look at the equation again.
Okay.
Right? You can see that it ultimately depends on the amount of electrons that is present. Right? So maybe increasing concentration could increase maybe the rate of the reaction, for example.
Okay.
Right? But we have to be very clear, the amount of product or the substance that you get ultimately only depends on the amount of electrons that is given. Right? Which ties into the first law of Faraday, as you can see over there. Right? So there's some pointers that says the more electricity you have, the greater the amount of electrons, and therefore the greater the mass of the copper that's being deposited.
Okay, sure. So shall we take a look at, say, the formulas now?
Yeah, so how do we calculate the amount of electricity or the charge? There's this very important formula. I'm sure you've seen this before. It goes like Q is equals to IT. So the two variables you must be comfortable will be I, which is the current in amperes, and also time, which is always in second. So make sure you do your units conversion properly.
Yes, nice.
Mr. Leong?
Okay. Wait, what's happening here? So you suddenly become an electron.
I'm an electron. So
okay.
do you know that electron carry charges?
Okay. Okay. I've just received 1.06 times 10 to the power of minus 19 coulombs, right?
Yes.
Okay.
So that's the amount of charge on one single electron.
Okay.
Okay, what if there's 1 mole of electrons?
Wait. 1 mole means you have, what, 6.02 times 10 to the power of 23 U's?
Yes.
You have a lot of U's now?
Yes.
And we're going to see how much charge do I receive, right?
Yes.
Okay. That becomes even more. So what's going to happen now is, what's the charge that is being transferred to me? The number that I was talking about will have been multiplied by the Avogadro's constant, right? So that's why you have the second formula over here. The amount of charge that you transfer using 1 mole of electrons will be given by F equals to LE, right? So the amount of charge I receive is known as 1 Faraday.
Yep, so just remember 1 Faraday is equals to 96,500. Very important values for you to do calculation.
Okay, sure. Shall we look at a question to help us to illustrate all these ideas?
Yes, all these are theories. Let's put into application. Okay,
so whenever we look at the electrolytic question, right, I think the steps will still be the same. Yes. So first things first, you have to determine what are the ions that are present inside the electrolyte, and then after that we have to determine where the ions are migrating towards which electrode. And of course, we have to go through the whole process to see which of the ions of the species are going to be preferentially discharged. Yeah. Okay. Now, for this question itself, they are actually quite kind because they tell us that we're going to see a mass of silver, and that's going to be deposited at the cathode. right? They've already done the steps for me. They realized that the Ag plus from the electrolyte is going to get discharged to give me solid silver. Okay, now the question actually gives me my current I, okay, as well as the time over here, which I have to be a bit more cautious because the unit seems to be wrong. What's the units again, Mr. William?
Seconds.
Must be seconds. It's like a physics SI units, right? Okay, so what we'll do over here is we're going to use the standard formula, first of which is I'm going to calculate the amount of charge that is being passed through the circuit. Q equals to IT. Using the formulas, you should be able to get 450 coulombs, right? Now, based on that, I will need to find out the number of moles of electrons that's being transferred. So, Mr. William, can you run us through how do we normally do that then?
Yeah, always remember 1 mole of one mole of electrons is 96,500.
Okay.
So right now we have 450, right? So you just divide by 96,500, you will know exactly how many moles of electrons there will be present, right? So it's always calculating the charge, then changing it to the number of moles of electrons.
Okay.
And the next thing to do, as we discussed earlier, the amount of products that you get always depends on the amount of electrons that's being passed through. So it's so important that everyone writes an equation, a balance equation. And the significance behind the balance equation is for us to see the mole ratio between electrons as well as silver. Right? So you can see it's a 1:1 ratio, which means the amount of electrons that's being produced must have been the same as the amount of silver that's produced. Right? So once you have the number of moles of silver, simply just multiply by the atomic mass, and there you go. This is the answer, 0.503. That's it.
Now, what happens if the question wanted you to connect another circuit again, right? So this is what we call connection in series, means that the cells are actually going to be one after another, right? So that's what's happening on the second question. There is another beaker which is using a different electrolyte altogether. Okay, there's nickel sulfate, and once again, the methods are going to be the same. You have to tell me what are the things that are going to migrate towards which of the electrode, and of course, we're going to see which one's going to get discharged using the E0 values, right? Now, this question, once again, they're quite kind. They're going to tell us that nickel is going to get deposited at the cathode again. So we're going to write out the half equations. And one of the most important ideas about this kind of circuit where you have your cells connected in series is the fact that the number of electrons transferred must always be the same. Okay, so whatever that you see over here will be transferred onto the second cell altogether. Okay, so what we're going to do is same thing as what Mr. Williams said. We're going to write out the half equations. The main reason is because I want to take a look at the mole ratio. Now, we already know that the number of moles of electrons is this, okay, 4.66 times 10 power minus 3, and we want to find out the mass of the nickel, which means that I must use stoichiometry to find out the number of moles of nickel first, and then after that you multiply by the atomic mass to find out the mass eventually. Okay, so the learning point for this question over here is that the number of moles of electrons transferred for any kinds of electrolytic cell in series will always be the same.
Okay guys, that's it for this video. We will shock you in class.